This chapter 27 is actually a pair with the next one. In this one, the analgesic trial introduced before is analyzed but through the binary version of the outcome. In chapter 28, we go for the full ordinal version, and then we see what is the same, what is still possible when we analyze the 5-point ordinal outcome rather than the binary outcome of the analgesic trial. And just like in chapter 26, we will illustrate a variety of methods that one can use for the binary repeated outcome that we are faced with here. So, the binary outcome is, of course, created from the 5-point ordinal outcome by declaring everything 1 if it's very good, good, or the medium category, and 0 otherwise, so that would be very bad and bad. The marginal regression relationship will invariably include time, the square of time, and then the covariate denoted by X, which stands for pain control assessment at baseline. And then the same relationship, but supplemented with a random effect, a random intercept in other words, will be the basis of our generalized linear mixed model. And depending on the model we are considering, again, we will be using a correlation or an odds ratio parameter to capture association. So first, we will consider first-order generalized estimating equations with its 2 sets of standard errors, model-based, i.e. naive, empirically corrected, i.e. robust. And here it's possible, it's consistent with the design, in other words, to consider the following working assumptions. Independence and exchangeable, I would say of course, because we can always consider them, which doesn't mean that we should consider them or it's the best choice, but it's very hard to imagine a situation where they would not be consistent with the design, which is not the same as them being accurate, correct, or anything like that. AR1 we can consider here too, because we have balanced longitudinal data. There are 4 measurements taken even at equally spaced time frames, 3 months apart. So that means 3 months into the study, 6 months, 9 months, and 12 months into the study. AR1, in other words, is one that is perfectly coherent with the design and so evidently is also unstructured. So, what we see here is the parameters estimated, the fixed effects, beta 1, beta 2, beta 3, beta 4, representing the regression relationship. And then under independence, there is, of course, no correlation parameters, or if you wish, it's equal to 0, but it's not estimated from the data. Exchangeable produces a working correlation of 0.22, AR1, 0.25, but that, of course, cannot be directly compared. Under exchangeable, every pair of outcomes has a correlation of 0.22. With AR1, it's 2 measurements 3 months apart, but if we go 6 months apart, it's 0.25 squared, and if it's 9 months apart, it's 0.25 to the third. And then under unstructured, we see a correlation structure with 6 parameters, 1 for every possible pair that is occurring. And we do see that there is maybe not a very clear decay. Also, we see a phenomenon that we hadn't seen before, that is the correlation between the last 2 times is much higher than between the others. In other words, near the end of the study, there seems to be a stability in the outcome. Again, it's very likely that this last correlation structure is much closer to the truth than the others. Now, that's all nice and well, but if we look at the distinction between the model-based and the empirically corrected standard errors, we see throughout that there is actually very little difference. Also, the fixed effects don't seem to be affected too much by which correlation structure that we use. And then, to summarize the correlation structure, bringing nothing new compared to the previous page, but just organizing it a little differently. In the exchangeable case, all correlations are the same. Here you see the decay that you would expect, of course. And then in the unstructured case, we get the 6 correlations that show the somewhat surprising, but maybe not, feature that the last 2 occasions are much more highly correlated than others. And then there is alternating logistic regression. Now, we have applied that before. In the toenail data set, we did not use that on the NTP data, but here we will illustrate not just one, but 3 different ones. There is exchangeable, and then there is unstructured, which is called full clustered in the software implementation in SAS, but that's a technical note, but full clustering is nothing but unstructured. And then there is a very important feature that we have not illustrated elsewhere, that is the user-defined design. And why would that make sense? Well, here we might say, maybe all of those correlations are equal, and this one is higher than the others. So we could parameterize it accordingly. That's not one of the canned structures. It's not one of the predefined structures, but it is a useful one nevertheless. So what we do see here is the log-odds ratio under exchangeability. Again, that's similar, I should say, as exchangeable with GEE, but the parameter is not directly comparable. Then we have the log-odds ratios for the full clustering or unstructured case, and also here you see that the last one is higher than before, in line with the correlations, but again, not something that is directly comparable in terms of magnitude. And then we have the odds ratio structure that we define ourselves with 2 parameters, which is 126 for all possible pairs, except for the last one, where it's 126 plus 1.17. So from that last model, if we go for that model, we conclude that the common log-odds ratio between all but the last pair is significantly different from 0. So an odds ratio significantly different from 1. And we do see that the add-on parameter, the additional parameter, is also significant. So we can say that the correlation between times 3 and 4 is, or the association, or the odds ratio, I should say, is significantly higher than between the others. Okay, so what does that mean for the odds ratios? Well, as I said, they're either all the same, or that's something we can actually formally test for, because you can compare, you can conduct a wall test to see whether the 5, let's call them original initial correlations or odds ratios are equal, or whether I also should distinguish between some of them, making the model a bit more complex. And that is not reported here, but it's reported in the book. And if we do that, then we say, okay, the first 5 are the same. I'm saying the same as I said on the previous page. And the last one is that same value plus an excess. We've seen the numbers on the previous page, 126, 117. But if you translate that on the odds ratio scale, of course, because of the exponential nature, it's a bit more dramatic. The odds ratio is 3.5 between all pairs except for the last, at which time it's 11.5, more or less. Okay, odds ratio matrices or tables, they're not really matrices, because matrices come with the connotation that you can do the usual matrix operations, positive definiteness, etc. No, odds ratios don't, or log odds ratios, they don't fit in the same framework, but we can organize them into a, let's say, array structure nevertheless, and that's what's done here. And then we go to a whole plethora of GE as well. Ordinary logistic regression can be considered, why not? Which is like GE with independence working assumptions, but where we take the assumptions seriously, which is hard to defend. Standard GE once more, parenthesis GE once more, the linearization method once more, and ALR. And we can do that for exchangeable working assumptions and then produce the various parameter estimates. So here you see a summary of all the GEs, including logistic regression. And while we would say logistic regression is by definition not correct, not the right thing to do. In this case, we learn, but only after the facts, of course, if you compare it with GE, that, yeah, if you would look at baseline pain control assessment at baseline, if you base your inferences on logistic regression in this case, or on proper GE, which is preferable, of course, the difference is nevertheless minor, unlike in the toenail data set. So am I saying you can use logistic regression? Actually, no. Because using logistic regression would be using it on its own terms, not comparing it to something else. But how would you know that your logistic regression works well if you didn't compare it to GEE? So the advice is, if the data are correlated, take the correlation into account. If the correlation is so weak that it doesn't make a difference, fair enough, you have at least given it a chance to play its role. So in that case, it's better to include working correlations or whatever when it's not necessary than the reverse error where you do ordinary logistic regression, but there is a high correlation, you completely ignore that and you make a terrible mistake. That's much worse. Okay. And across the board, even though the association structure is a little different in some models, we do see throughout that we get, let's call it, the same qualitative conclusion. And I think, except for logistic regression, the same quantitative conclusion with all of the modeling approaches. Finally, the generalized linear mixed model. Well, we can use the SAS procedure GLIMMIX. You can use NL mixed, of course, MQL, PQL. We can use the NL mixed with adaptive, non-adaptive, and also GLIMMIX if you wish, quadrature with different numbers of quadrature points. And here, just for the sake of comparison, I will also use MLWin, standalone software package, but which does allow, except for PQL1, also PQL2 as the Taylor series approximation method. And the claim is that PQL2 is much more complicated, but it's implemented by Goldstein, so that's not our concern here. Not only that, it's also, and that's the most important thing, much more accurate. And then there is MIXOR, developed by Hedeker and Gibbons, which stands for Mixed Effects Ordinal Regression. So it's ordinal data with random effects, but we don't have ordinal data here in this chapter, no. But binary data, of course, is an almost trivial special case of ordinal data, so we can also use it here. Okay, so first the integrand approximation, MQL and PQL. Also here, you see that the difference is not dramatic, but noticeable. And you see that especially if you look at PQL2 here under MLWin, those estimates are considerably different. Again, not as dramatic as in the toenail data set, but they are different. The variance of the random intercept here is 2.6. It was 1 point something in the NTP data, so relatively low. It was 16 in the toenail data set, so much higher, but already with this value here, we see the downward bias with PQL1, with MQL, etc. If then we go to numerical integration, well, I should have said that non-adaptive quadrature with a small number of quadrature points is slightly different from the other three, but the other three produce the 2 decimal places exactly the same result, which is why they're not repeated 3 times, so not adaptive, non-adaptive, Q is 10, Q is 20. 3 of them are the same, they're placed under Roman 2 here in this case. But even if you compare to number Roman 1, I would say there is qualitatively no difference. And MIXOR and full numerical integration are extremely similar, and that is MIXOR uses full numerical integration, but it does apply a approximation to the standard error calculation, which is why standard errors are not as good as they could be. But in terms of point estimates, it's not a surprise because they use very, very similar algorithms that you get very, very similar results. So The ratio between the random effects and the marginal parameters, now if you calculate it, is, I'll slightly exaggerate, 1.5. It was 2.5 in the toenail data set, entirely due to the different variance of the random intercept between these two models. Okay, and that brings me to the end of chapter 27, which analyzed the analgesic trial, but in its binary version. In chapter 28, we will do the same, but for the full ordinal outcome.